Hello, I'm Armando Vela from Pivot Analytics Incorporated, and we analyzed the US and Nevada's COVID-19 cases. So what was the COVID-19 data that we gathered? The Nevada case data, we got that from the State of Nevada's Department of Health and Human Services webpage. For the US case data, we got that from the CDC control webpage. The time frame for Nevada is from March 15th through July 16th, while US is from January 22nd through July 16th. So for the Nevada case data, first COVID case did not occur until March 5th, 2020. And as we can see here, the number of cases actually has grown exponentially since the start. With that, there seems to be some wandering behavior represented in the realization, and that is further identified as we can see within the parser window has a max frequency at 0, as well as there are slowly dampening autocorrelations. Based on this evidence, we're going to assume this and model this data as if it were non-stationary, and to account for this, we're actually going to be conducting some transformations to properly model and fit the data. One other thing that we'll be doing is removing the first 20 observations since they've been hovering around 0 and we don't want to skew any of our forecasts. So part 3. So as you can see here on the table to the right, this is the first difference table. It gives us the realization and so forth. Well, we did notice that there was some seasonal period of 9, so we wanted actually to test that out as well, just to see if it would actually provide a better fit. And this table right here, we can actually see the P's and Q's for the first difference only data set with the first difference plus that seasonal period of 9. And we got these using the AIC5 package within TSWGE. So after running the model and getting all the fees and thetas through each using TSWG's estimate function, we were able to identify that the first difference, P equals 10, Q equals 0, actually provided the best fitting model. It had the lowest mean, minimum, and median scores when comparing the rolling ASC scores amongst the 6 different models we ran. We're actually moved forward with forecasting the next 7 days as well as the next 3 months using the ARIMA 1010 model. As you see within these images, for the ARIMA 1010 model, 7-day forecast seems appropriate, while the 90-day forecast averages out at around 2,000 cases per day. So for the US case data, the first case did not occur until 1/22/2020. Similar to the Nevadas, the number of cases has grown exponentially from the start. And there seems to be some wandering behavior represented in this realization as well. So with that, similar to Nevada's case data, we also noticed that there was a max frequency at 0 within the parsing window, as well as slowly dampening autocorrelations. We went ahead and modeled the data as if it were non-stationary and conducted some transformations on the data. Furthermore, the first 60 observations were removed since they were also hovering around 0. So we went ahead and estimated the P's and Q's on a first difference data set as well as a first difference plus seasonal period of 7. The reason why we added a seasonal period of 7 is because we noticed that there was actually a strong period within the autocorrelations as well as the parsing window. The P's and Q's that were identified using the AIC5 function can be found within this table. After reviewing the rolling ASC scores, the first difference plus seasonal model with P equals 6 and Q equals 2 provided the best fitting model. We went ahead and moved forward with the forecasting using this model. As you can see within the images, the 7-day forecast seems appropriate, while the 90-day forecast continues on until it equals 200,000 cases per day by the 90th day. The plan for the remainder of the analysis is to use other univariate approaches to analyze the data, as well as conduct some multivariate analysis on the data as well. Any questions?